Hi guys, welcome to today's video, Rate and Extent of Reaction, Grade 12 Chemistry chapter. Chemical reactions happen every day all around us. Let's take a look at a couple of examples. First, we have milk left out the refrigerator. It gradually turns sour, as you well know. Next, we have a car that is exposed to air and moisture. It gradually forms rust. And lastly, we have fuel burning inside a car engine. The reaction happens in a fraction of a second. Now, all these three cases are chemical reactions. Each of these reactions is taking place at a different rate or at different speed. For the milk, it can take hours up to days maximum before it turns sour. For a car that's rusting, that's a process that can obviously take maybe months up to a year. And then for a fuel burning inside a car engine, that literally takes a fraction of a second. It happens very fast. All of these are chemical reactions, but they have different speeds or rates. For a chemical reaction to occur, we need to have first reactants. Those are your substances that are undergoing the reaction. And next, we need to have the products. Those are the results of your reaction, obviously. And now, reaction rate refers to how quickly or slowly the reaction is happening. We observe how quickly the reactants are reacting together or the products are being formed to know the exact rate of a chemical reaction. Let's take a look at oxygen and water reacting to form water. We have this chemical equation, as you well know. What we can deduce from that reaction is that we can observe the speed or the rate of that reaction by measuring the time it takes until there's no more hydrogen or oxygen in the vessel. That is, either one of the reactants is depleted. That is when the reaction is complete or it stops, and we can measure the time until that happens to know the exact rate of a chemical reaction. And now the term reaction rate refers to the change in concentration of products or reactants per unit time. That is the definition provided by the exam guidelines, and you need to write it exactly like that in your exams, as you well know. From the definition above, we can see that we can measure reaction rate in two ways. First, with the products or with the reactions. Let's take a look at how you do it through reactants. For reactants, you go on and say depletion of reactants is equals to number of moles of reactants used divided by time. That is measuring reaction rate using the reactants. And next, let's take a look at how you can measure reaction rate using products. You go on and say formation of product is equals to number of moles of product formed divided by time. Now let's take a look at an example. We have the following reaction taking place. After 5 minutes, 12 grams of magnesium has been used. Calculate the rate of this reaction. For this particular example, we're going to have to use a reactant to measure the rate of this reaction, because that is the substance that I've been given a little bit of information about. And I'm going to go on and first calculate my number of moles. I'm going to go on and say the number of moles is equal to mass divided by molar mass. And substituting in my values, I get 12 divided by 24,305. You get the molar mass from the periodic table, and that will give me a value of 0.49 moles. Next, I'm going to convert that 5 minutes into seconds. And to do that, I'm going to say 5 minutes multiplied by 60 seconds to give me 300 seconds. And finally, I have enough values to substitute into my equation to get reaction rate is equals to 0.49 divided by 300 seconds to give me a value of 0.00163 moles per second. And that is my reaction rate. Now let's discuss collision theory. You should have noticed by now that some reactions take longer to occur than others, and I did mention this to you previously. Keeping in mind that for a chemical reaction to occur, particles have to collide first. Collision theory explains the difference in reaction rate for different reactions. Let's take a look at these three cases. First case is an ineffective collision case. That is where the particles collide, but they do not have enough energy to react. They are in the right orientation, but they don't have enough energy, and hence they will bounce off each other and go their separate ways. Now let's take a look at the second case. That is when the particles collide with enough energy, but in the wrong orientation, as you can see from my diagram. And again, the particles will bounce off each other and go their separate direction. And the final case, that is the effective collision now. That is when particles collide with enough energy and in the correct orientation. That is when a reaction occurs. And now, collision theory states, as per your exam guideline, a model that explains reaction rate as the result of particles colliding with a certain minimum energy to form products. Therefore, according to the collision theory, in order for a reaction to occur, particles must first collide, that is a minimum requirement. After collision, they must have enough energy. And thirdly, they must be in the correct orientation at the moment of impact. That is when a successful collision happens. Successful collisions are the ones that break the bonds of the reactants and form new bonds of the products, and hence successful collisions are prerequisites for a reaction to occur. Without successful collisions, we cannot have a chemical reaction. Let's take a look at factors affecting reaction rates. First, we have the nature of the reactants, that is, different substances have different chemical properties and hence react differently under different conditions. Next, we have the surface area. This is only applicable on solids. Larger surface area increase reaction rates since more particles are now more exposed to collide. A physical example of this on our everyday life is maybe, let's say you wanna mix sugar with water to make sugar water. If you grind the sugar into smaller, finer particles, you are increasing the surface area of the sugar, and hence smaller particles of the sugar will react or dissolve faster on water as opposed to one block of sugar, and hence when you grind it, you are increasing the surface area and hence increasing reaction rate. And next we have concentration. That is, higher concentration increases reaction rate because now more particles occupy the same volume, and hence the chances of particles colliding have been increased, and hence reaction rate increases. And next we have pressure. This is only applicable on gases. Higher pressure increases reaction rate as more gas particles are forced close together, and again increases the chances of a collision. And next we have temperature. Higher temperature increases reaction rates as increasing the temperature increases the kinetic energy of the particles, and hence increasing the chances of more particles with enough energy to react. And lastly, we have a catalyst. A catalyst increases reaction rate without being used up in a chemical reaction. Let's take a look at an example. Write a balanced chemical equation for the reaction between iron and oxygen to form iron oxide. Also name 3 ways in which the reaction rate can be increased. There is the chemical reaction. You can see it on my screen. First, let's analyze that reaction. We have iron, that is a solid, and we have oxygen, that is a gas. How can we increase this? We know that because iron is a solid, we can increase its surface area, and for gas and for oxygen, we can increase its concentration or pressure to increase the reaction rate. You can choose any 3 factors. Here are the factors that I chose. First, I went on to say increase the temperature. Obviously, more particles will have higher kinetic energy. And next, I went on to say surface area, as I've previously mentioned. And lastly, I went on to say increase concentration of the oxygen because it is a gas. Now, let's move on to measuring reaction rates. We use the following methods to measure reaction rates. First, we use the volume of the gas produced. If it is that kind of a reaction, we measure how fast gas is being produced over time if gas is one of the products of the reaction. Next, we precipitate reactions. That is, measure how quickly solids are being formed or how solids are precipitating. And next, we observe the color change to see how fast a color change occurs during the reaction. And next, we have change in mass. And this is the last one. We measure the loss of mass over time if a gas escapes from an opening system. Earlier, we discovered that in order for a reaction to occur, particles must collide, and only some of these collisions are successful. One factor affecting the success rate of collisions was energy, kinetic energy to be more specific. Only a fraction of the particles will have enough kinetic energy to react. There is a minimum energy required for a reaction to take place. This energy is known as activation energy, and hence activation energy can be defined as the minimum energy needed for a reaction to take place. Now let's take a look at some graphs and how we interpret them. Take a look at the graph on my screen there. We have the lower temperature curve sketched on a white color, as you can see, and a higher temperature one sketched in an orange color, as you can see. And we have the vertical dotted line, that is my activation energy. Now, For the white line, if you look for the particles with enough activation energy, there are very few, but as soon as the temperature rises and we move on to the orange line, more particles have now energy that is greater than activation energy, and hence the chances of a successful collision are increased. Writing this down, even at a fixed temperature, the energy of particles differ. Increasing the temperature increases the average kinetic energy of the particles, and hence increasing the temperature increases the number of particles with enough energy to react, or with enough activation energy, and hence a higher percentage of the particles can react, now making the reaction faster. Now let's move on to discuss endothermic and exothermic reactions. First, we have endothermic reactions. That is a reaction where reactants have lower energy than the product, and hence for this type of a reaction to occur, we need to have reactions plus energy to form products. In other words, this type of a reaction absorbs energy from the environment to form the products. And next, we're going to discuss exothermic reaction. This is a reaction where reactants have higher energy than the products. And in order for this reaction to occur, we need to have reactants reacting to give us energy plus products, and hence this type of a reaction releases heat energy to the environment. That is the plot for an exothermic reaction. Now let's take a look at how catalysts work. A catalyst lowers the activation energy so that more particles have enough energy to react. How do catalysts now lower the activation energy? First, by orientating the reactant's particles in such a way that a successful collision is more likely, and lastly, by reacting with the reactants to form an intermediate that requires lower energy to form the products, and hence the term catalyst can be defined as a substance that increases the rate of a chemical reaction without itself undergoing a permanent change. And that brings us to the end of this lesson, and hence to the end of the video. Please do comment below on which chapters you want me to cover next. But for now, thank you for watching. To support the channel and help more students access free lessons, please like the video and subscribe if you're new to the channel. For additional learning materials and updates, visit our website using the link in the description below. Keep studying hard, and I'll see you in the next one. Cheers.